Okay, I'm Dr. Corkum, and I'm just going to take you through using Phase 2 finite element software to do a very simple model of a beam with a hole in it. The Phase 2 software, I introduced it in another video, but it is a geomechanics finite element software, so it does use the typical units and sign conventions for geomechanics, which is typically MPa, and stresses are negative in compression. Okay, so first I'm going to open up the Phase 2 software. And the first thing we're going to do is to adjust the project settings. Okay. So there's various settings you can adjust here. We're going to keep a plane strain model with stresses in MPa. And we're going to include 3 stages in the model. So it's going to have 3 load configurations. And we can give them names. And the first one is going to be with the 50% of the load. Then we're going to have 100% of load. And then we're going to have 100% of load and cut the hole in the section. So by naming them all, it makes it a little bit easier to follow later. And okay, well, actually I want to make another change here. Project summary. Add some details about the project. So give it a title. Put your own name in there. And some information about us. And you can add some other comments too. Okay. Now you can see these little tabs here. They really lay out the order in which most projects are put together. I'm going to start off building the geometry of the model. So it's going to be pretty much a rectangular section with a little tab on the top to put a load on. And so I've drawn it all out, and it's sitting in front of me, and I'll put together the geometry here. So first I'm going to click on Add External Boundary, okay, in this boundaries area. And then you can either do it graphically, or you can enter the coordinates of the vertex or nodes directly in a box in the bottom right with a space in between. Okay. So first I'm going to enter the XY coordinates of the lower left-hand corner of the section. And then push C to close the boundary. And then we're all done. So we'll just zoom in on that. Okay, so I have a rectangular section with a little tab that I'm going to attach some loads to later on. Okay. So the next thing I want to do is we have to build in all the possible stages at the beginning. So we're going to put a circular hole in the section. And so we can draw an excavation. Okay. And then down the bottom right it gives us options, table, circle, etc. I'm going to type I for circle, and it'll bring up some options here. And I'm going to enter it. I want to enter the center plus a radius. And I want the radius of the circle to be 0.15 meters. And the number of segments, you know, a circle in finite element is really made up of a bunch of linear segments. And I'm going to pick, say, 32 segments. Okay, and now there's my circle. And I'm going to enter the coordinates of the centroid in the bottom right. And I want it to be at x of 0. This model is set up with the center line at 0, x is 0, and y of 0.25. There we go. There's our circle. Okay. Okay, and I'm going to want to, when I mesh this, I'm going to want to put a very refined mesh around the circle. So I need a little bit of help. I'm going to have to put a boundary in here to divide the model into different regions of meshing. And I'm going to do that by adding a stage boundary. And I'm going to make it about the same distance above the circle as there is below the circle in the model. So I'm just going to click on there and drag it across. Click on the other boundary, then right-click and push done. So there's a little boundary there. So I can mesh this more finely than the area up here. Okay, so now is a good time to save your model. You have enough put in that you just don't want to lose it. So File, Save As, and I'll call this one In Class Example. Okay, so it's saved, and we shouldn't lose it. Okay, the next tab, it says Material and Staging. So it wants us to put the material properties and material or constitutive models that we're going to use. We're just going to use a linear elastic model here. So this dialog box here, Define Material Properties. Click that. And the first material, material 1, we can call it whatever we want to. I'll call it metal. Okay. And we can make a different color, whatever we like. I'm going to use yellow. And we can have a failure criterion if we want to account for yielding or failure of the elements, but I don't. I'm going to keep it elastic. And I'm going to use a Young's modulus of 50 GPa or 50,000 MPa, and I'm going to keep the Poisson's ratio at 0.3. So because this is material 1, which is the default material, when I accept this, it should automatically update the model to that yellow material with these properties. Done. Okay. Now, we have the 3 stages where we're going to load it all together to 50%. You can see the stages are in tabs in the bottom left. And then we can load it to 100% in another stage. And then we're going to cut this hole in the section. So we want to cut this hole for stage 3. So you can assign the material properties tab. This is when you can assign different materials if you have multiple materials. But we're going to excavate or cut this hole. Okay? And watch, I'll cycle through the stages, and you can see it's only cut in stage 3. Okay. So it's the material is solid in stage 1 and 2, and then in stage 3 the cut has occurred. Good time to save. All right. So the next tab is the mesh, and that can be fairly involved. We're going to first discretize the domain by pushing this button. Okay. And you can see it put a bunch of nodes around it. And then when we push mesh, it will basically use those nodes to make some kind of graded mesh automatically. See, watch this. So there you go, made a mesh. Not too bad. Personally, I'd like to see a lot more refinement in that mesh. In particular, where we're going to add the load here, there's only 2 zones. That's quite poor. And I could use a lot more refinement here, maybe twice as much. So I'm just going to remove the mesh and discretization, and it'll start over. I can open this dialog to get the mesh set up. And it can give us lots of different options, a graded mesh or a uniform mesh or gradation factors, which is how much it changes, and the default number of nodes on all the excavations. So that's one way to do it. Another way to do it is you can just build your mesh, and then you can drop this down and you can tell it to increase the discretization density of the mesh that exists or increase the mesh element density. First, let's increase the discretization of the whole thing. So then you just use your mouse to select the domain you want to deal with. And I'm going to use the entire model. Okay, so that made it a lot denser. Now I'm going to try and increase the mesh density in the middle area because it seems to grade more than I'd like. I'd like it to be more uniform. So I want to increase the mesh element density in this area. There we go. That looks pretty good. Quite happy with that. Just save that one. Next tab is support. That has to do with ground support for tunneling and rock mechanics. And there's one on groundwater. We're not dealing with that. We're dealing with more of a mechanical section, like a structural section. And then the final tab is the loads and restraints. So this is the boundary conditions and what kind of loads we're going to put on it. Well, first off, it automatically put these fixed boundary conditions everywhere. And I don't really like those, so I'm going to get rid of all of those. Okay, delete boundary condition, and then I'm going to drag a window over everything, select it all, and just push enter. So that deleted all the boundary conditions. So in this case, I'm going to put just one boundary condition. I'm going to say that this model is symmetrical vertically. So the model that exists on the top is the same thing as a reflection below it. And I'm going to do that by putting roller boundary conditions on the bottom boundary line. So I click it and I can just push enter, and there's roller. So it's free to roll left and right without constraint, but it can't move vertically. And there's no other boundary conditions. Okay. Now I'm going to add a load to the top up here. And we want to do that in the first stage. So on the bottom left, click on stage 1. And then we're going to select a uniform load. Add a uniform load. And we're going to make a vertical load of 10 MPa. And we want the load to be acting upwards. So in this case it says positive is down. We want it to be negative upwards. And we're going to stage the load because we said we wanted 50% of the load in the first stage and 100% in the second stage and 100% in the third. So these factors are out of 1 instead of percent. So 0.5 times the load in stage 1 and the full load in stage 2 and 3. Okay, so I think we have everything. We push OK. And now the next boundary line that we click on, that stress is going to be applied to it. So we're going to click on this top tab, and then we're just going to push Enter. And you can see there, it was a 10 MPa stress, and we applied it in 50% in stage 1 and 100% in stage 2, acting vertically upwards. So everything looks pretty good. We'll save the model there. And now we want to solve the model. We just push this compute button here and it'll do all the solving automatically. So here we go. This is a very small model. It'll solve in maybe a second or so. Okay, the model is running, and there it is. It's saved. Sorry, it's solved, and it saved the file with all the calculations in it. And now we'll click on the Interpret button to have a look at our results. Okay, it opens a new window. And you can see it looks just like the model building stage. This is the interpretation program, I guess you'd say. And again, in the bottom left, you have the different tabs. Okay, and you have the model results. And over here on the left, you have contour interval legend, and we're showing contours here. And this drop down in the middle, it helps you determine contours of what parameter. So displacements, strains, and stresses. So we're going to just look at vertical stress, or sigma YY. So that is your contour of vertical stress. Again, because it's a geomechanical modeling software, tension is negative. So we got a light blue across the top here, which is around 5 MPa negative, so that looks right. Okay, that's exactly what we expect. And if you remember from class when we talked about St. Venant's principle, the stress distribution becomes uniform after a length equal to about the width, which is somewhere around here. And you can see it does become about uniform. Okay, so this model, the width here is 0.1 meters, and the total width of the model is about 0.5 meters. Okay, so 0.1, let's go to the 100% of the load. 0.1 times 10 MPa is 1 MPa. 1 meganewton. Okay, 1 meganewton. Okay, and if we have 1 meganewton across 0.5 meter wide section, that corresponds to a stress of 2 MPa. Okay, so this green is around 2 MPa, and it's a fairly uniform, similar to St. Benant's principle. So that looks to be right. Okay, and then finally we can see the effective stress distribution from cutting that circle. And you can see all the stress concentrations around that circle. And remember, it's symmetrical, so there's actually another section reflected down below with another circle down here and another load applied to the other end. Okay? So one very nice capability of the Interpret viewer is that you can plot some of the data. So we'll add a material query here, say right around here, which lets you draw a line, okay, and then push done, and say we want to know the data. We want the data printed at 10 different evenly spaced locations on that line. Okay? And now that allows us to plot the data. So we right click and say graph data, and it'll make, and we can graph all the stages in one plot. So there, it makes another tab, so you have your model in one tab and this plot in another. It's very much like an Excel plot. So you have distance along that line, okay, 0 to 0.5, and the vertical stress value, okay, for stage 1 in blue, stage 2 in red, and stage 3 in green. So stage 1 is, we got 1 MPa of stress, and that represents 50% of that load, and you can see it's very uniform, so everything agrees. St. Benant's principle is correct, and the load value agrees with what we entered into it. The next stage, 100% of the load or stress, you can see is 2 MPa in tension. And the third stage, you can see there's a real distribution happening because of the influence of that circular hole. So that really proves that the model is behaving the way you intended it to, and the results are as expected. A couple of other things you can plot. You can display the deformed shape. It's an exaggerated deformed shape of the model. And you can plot displacement vectors to show how the model displaced in each stage. Okay. So that sums it up. I think it shows you basically how the Phase 2 finite element modeling works for this sort of random section. And yeah, you can apply the same approach to many other different types of models.